So for those that were not around last time, we started the is it the coup on isomery and stereoisomery. Now we said an isomer is an organic compound, or yeah, exactly, an organic compound that that is made up of two parts. The first part is that that organic compound must be different with the other. That organic compound must be different with the other in two forms. That is, the organic compound must be similar in the chemical formula, that is the formula brute, but should be different in the structure formula. That is what makes up an isomer. Then we said there are three types of isomers that we're going to look at. That is isomer de constitution, isomer de configuration, isomer de conformation. Now, with isomer de constitution, this is what you guys have been learning all along from Zambia. We have isomérie de position, isomérie de fonction, isomérie de chaîne, where we have the different aspects of how the enchaînement is and how the function is distributed for a hydrocarbon, and how is it the function? Yeah, the function, the chain, and the position. Position beat a double liaison. You have got have an example here. You have like butane where the position is at position number 1, and you have butane at position number 2. When you talk about functions, we have ethanol and methoxymethane. So the idea is they have the same formule brute. Formule brute, c'est la même chose avec chemical formula. Formule brute, which is this, c'est la même chose avec chemical formula. Their structure is what is different. Their structure is what is different. So isomery de constitution, this is what you guys have been looking at all along. Isomery de constitution, all along you've been looking at isomers that are different in terms of their function, isomers that are different in terms of the position, and isomers that are different in terms of their skeleton. Now there's a new aspect, that is isomery de configuration. Now isomery de configuration, also known as isomery steric, this is where you have the breaking of bonds, the breaking of covalent bonds to form new ones, and the breaking of bonds to form new ones causes the formation of isomers. Yeah. Then there's also what you call isomery de conformation. Now, conformation, this is where you just have instead of you breaking the bonds, you just have the twisting and turning of these liaisons to make conformers. We call them conformers. Now, in today's study, we're going to look at what you guys have been hearing me say all along: enantiomers, their stereoisomers, epimers, and all those things. So we are going to look at the principle of chiralité and enantiomers and stereoisomers. Yeah. So a compound is chiral when it satisfies two conditions. A compound is chiral when it satisfies two conditions. Now, before we go to the two conditions, we are supposed to understand that a compound being chiral is supposed to be non-superposable. It's supposed to be non-superposable. So the example that they usually give for chirality is your left hand and your right hand. So if you get your right hand, or you take your right hand and place it over your left hand, in whatever orientation, either 3D, 2D, it will never be superposable. What I mean by superposable is having the thumb facing the thumb, and the apex, is it what you call this finger, the middle finger, the pinky, and all those fingers facing each other. What I mean by facing each other is not like your left hand and your right hand are, like you can see in the diagram here. They will never be superposable. So what I mean by superposable is this thumb being this side. This thumb, you bring it this side here. It will never be superposable. The hand will never be superposable. So in other words, when you place your right hand or your left hand on a mirror, it forms an image. And that image is, that is, if you place your right hand, it forms an image of your left arm. If you place your right arm on a mirror, it forms an image of your your left arm. So the image that is produced, is what we are calling an enantiomer. is what we are calling an enantiomer. So an enantiomer is basically a mirror image of another organic compound. Now it's organic chemistry, of course. So an enantiomer is a mirror image of an organic compound. So take, for instance, we have this one here. We have this organic compound here, A. When it is placed on a mirror, it forms this one here. So what is in front becomes, it changes direction. What you are seeing here is the mirror image. This is a mirror image of this one here. Now there's a rotation of 180 degrees, so you find that they are almost like the same. But these two compounds, that is A and B, are what we are calling enantiomers. Enantiomers. So the mirror image, that is A and B, are called enantiomers. So A is, for example, like our left arm, and B is the mirror image of our left arm, which is our right arm. So because there's a rotation of 180 degrees here, so we come back to this molecule. But the mirror image that we are going to consider will not be this one, because there is a rotation of 180 degrees. We are going to consider this one here, because what we are seeing facing, for those that were here last time, there is what you call the wedge and dash. What you're seeing on the wedge here, on the dash, that is a wedge with dashes, is now coming out of the page. It's now coming out of the page. Or in other words, what I'm trying to say is that there's been like changement. What was on the wedge, that is the board one, has now gone on the wedge with dashes. What was in the wedge, the board one, has now gone to the wedge with dashes. And what was on the wedge with dashes has now come to the wedge that is with a border line. So that is what happens on a mirror. That is what happens on a mirror. Take, for instance, you have the word ambulance. When you ambulance, is it written backward? When you put it on the mirror, you find that it's going to be written in the way it's supposed to be spelled. So this is the same thing that's happening here, because you have the hydrogen that is arrière. The hydrogen that is arrière, when you bring it on the mirror, it's going to be avant. And the hydroxide that is avant, when you bring it on the mirror, will be arrière. But these ones on the plane still remain the same. The two, that is the carboxylic function and the methyl, will still be on the plane. They'll still be on a plane. So that is the principle of enantiomers and chiralité. So now, for an organic compound to be chiral, it's supposed to satisfy two conditions. The first one is it's supposed to have it should not have, please take note, it should not have, they're here, it should not have what's this, a plan de symmetry, should not have any symmetry plan. The second one is it should not be superposable with its image. It should not be superposable with its image. So in other words, your hands are chiral. Your hands are chiral. Why? Because they are not superposable and there is no plan of symmetry. There is no plan de symmetry. There is no plan de symmetry. Then if an organic compound does not satisfy or satisfies one of the conditions, that is, it is superposable with its image, but does not have a plan de symmetry, it is called a chiral. It is called a chiral. It's called a chiral. So you have two conditions. That is, one, for an organic compound to be chiral, it's supposed to be non-superposable with its image. That is on a mirror, of course. And it should not have any plan de symmetry. It should not have any plan de symmetry. In a case where the two conditions are not satisfied, the organic compound is called, or the molecule is called achiral. If one of them is satisfied and the other one is not satisfied, they are called achiral as well. So, okay, so we have this one here. So we have an example of an organic compound that is on a mirror. This is 2-hydroxypropanoic. It has been placed on a mirror. Now, it is found that these two images, whenever you turn them, because like I said earlier on, stereoisomery is isomers in 3 dimensions. Isomers in 3 dimensions. That is where the stereoisomery comes in. This is isomerism. in 3 dimensions. So when you place this 2-hydroxyl propanoic, it's a propanoic acid, so it means it comes from the family of carboxylic acid. So if you place this 2-hydroxyl propanoic on a mirror, depending on how many times you're going to rotate it, the image you're going to produce will never, ever be superposable with its image. It will never, ever be superposable with its image. Then another condition, that is when you have only one carbon asymetric, si vous avez un seul carbone asymétrique, c'est-à-dire the compound is automatically chiral. If you only have one carbon that is asymmetric, the compound is automatically chiral. If you only have one carbon that's asymmetric. So the carbon asymmetric, that is a carbon atom that has got 4 different substituents. 4 different substituents. So you have the first one here. It's different from this one. It's also different from this one. And it's also different from the hydrogen. So it's automatic that a hydrocarbon or an organic compound that has only one carbon asymmetric, it will always be chiral. It will always be chiral. But for images or for organic compounds that have 2 or more, a carbon that's asymmetric, you are supposed to verify the 2 conditions. You are supposed to verify the 2 conditions. Are there any questions?
If you can just repeat the thing of asymmetric being the other one with one chiral and the other one not.
So we are saying for us to satisfy the principle or the notion de chiralité, we are supposed to satisfy, that is, 2 conditions. The first one is the molecule or the organic compound should never be superposable with its image. Should never be superposable with its image. So please, whenever I'm talking about non-superposable, just think of your hands. Think of your hands. When you place your right arm on your left arm, it will not be superposable. What I mean by not superposable, this is the arrangement we are talking about. This is the arrangement we are talking about. Then it should not have any plan de symétrie. Any plan de symétrie. So if it does not satisfy the 2 conditions, that is, if it does not have, if it does not satisfy the 2 conditions, that is the first one. It should not be superposable with its image. And the second one, it should not have any plan de symétrie. We are calling that a chiral molecule. But in a case where we have a superposable compound and we have a plan de symétrie, we are calling that organic compound achiral. We are calling that organic compound achiral. But there is another astuce. We are saying if you only have one carbon asymmetric in an organic compound, only one carbon asymmetric, like in the case of 2-hydroxyl propanoic, in the case of 2-hydroxyl propanoic, you are automatically having a chiral compound. You are automatically having a chiral compound. It was found from analysis that only having one carbon that is asymmetric, that is, you are going to have a chiral molecule. You are going to have a chiral molecule, which will not satisfy the 2 conditions. The first one is it will not be superposable with its image, and the second one is it will not have any plan de symétrie. So is it clear?
Yeah.
Okay. So now we go to the nomenclature part. So in Enantiomers and Isomers, we are going to have another type of nomenclature. So please take note. Pardon?
Yeah. Can you just also explain on the symmetric thing?
Okay. So what it means by symmetry is that there is what you call, there are different types of symmetries. There are different types of symmetries. There are those ones that cut the compound across. Where is it? Just a minute. You can have a compound that is like that. if there exists symmetry between this part and this part, that is in the case where the substituents at this part and this part are symmetry. You know what, you guys, you understand what I mean by symmetry? Like what is on the left hand side is as equivalent as what you are having on the other side. So if you have a symmetry that is cutting this molecule in between, if you have a symmetry that is cutting this molecule in between, and you consider that the left-hand side is almost as equivalent to the right-hand side, it means it does not satisfy this here. It does not satisfy this because we have a symmetry. We have a symmetry. But for us to have a chiral molecule, we are not supposed to have any symmetry, pen and pot. The symmetry can either be from your mathematics. Symmetry can cut the molecule there across like that, or you can also cut it like that, along like that. For as long as you are going to have a symmetry, if a molecule is going to have symmetry, if it's going to have symmetry, count it, it's automatically going to be a chiral. If it's going to have a symmetry, it's going to be a chiral. Then there are cases where we're going to have form meso, but I won't go as far as form meso for this lecture. There are those that are form meso. They have carbons that are asymmetric, but we consider them to be achiral. There are reasons why we consider them to be achiral. So now, in a case where we have this organic compound here, that is 2-hydroxyl propanoic. Now we have a carbon here. We have a carbon here. Now the carbon, if you look at how the carbon is oriented, if we were to draw a symmetry, we are all not going to have a symmetry because what is found on the left-hand side, or maybe let me say, what is on two, what is surrounding this carbon here, this carbon here, is totally different. There is no symmetry. There is no symmetry between this hydroxyl, is it this hydroxyl, and this hydrogen, and this methyl. There is no symmetry. So like I said, symmetry comes in as an aspect where what you have on your left-hand side should be equivalent or should match up with what you have on your right-hand side. So in our case, we have 3 different substituents. That is with reference from the carbon atom, which is asymmetric. We have 3 different substituents that are totally not symmetric in reference to the carbon atom that we have here. It is for this reason why they are saying all organic compounds that will have one carbon that is asymmetric, will always be chiral. It is for this reason, because we are saying for us to have one carbon that is asymmetric, it means the 4 substituents are supposed to be different. So here's another example. So a carbon bonded to so we say A, C, D. Then I'll give another example here. So A, B, C, D. So now we are saying a carbon that is asymmetric is one that has 4 different substituents. Now, if it has 4 different substituents, our rule is it is going to be chiral automatically. It's going to be chiral automatically. So therefore, this one here is chiral automatically. Why? Because the carbon that is asymmetric has 4 different substituents. That is A, that is B, that is C, and D. But in the case where you have 2 substituents that are similar, Now, because you're having 2 substituents that are similar, it disqualifies the compound to have a carbon that is asymmetric. So if it disqualifies that, now we're going to look at the aspect of, is it superposable with its image? Automatically, it shows that it's going to be superposable with its image in the sense that when you place this on the mirror, the A and the A, you won't see the difference. You will not see the difference. It's like you have, how can I put it? You have, O, you have O. You see, when you place O on a mirror, when you place O in front of a mirror, O does not change anything. O looks the same. O on a mirror, c'est la même chose. O does not change. It's the same thing. It still looks the same. Sometimes people make this joke, say, atuwapindamula zero, something like that. Zero will never change. Whether you orient it in any way, 3D, all those things, it will never change. It's the same thing here. Because you've got two identical substituents, that is A and A, that are similar. When you place them on the mirror, when you place them on a mirror, they will be the difference won't show. The difference won't show. In other words, this organic compound can be superposable on its image. It can be superposable on its image. Now, when you come to the aspect of symmetry, so it means the first rule here does not apply for this compound. It means it can be superposable with its image. It can be superposable with its image. Now, when you come to the aspect of symmetry, we said symmetry should justify that the two parts of an organic compound are similar in one way. Now, you only have this part that is similar. You only have this part that is similar. But on the other side, you have two different substituents. When you talk about symmetry, we are saying there should be an equivalent side. That is, what is on your right-hand side should be approximately equivalent to what is on your other side. That is what you call symmetry. That is what you're calling symmetry. But what if you have on your left-hand side is different from what you're having on your right-hand side? That does not mean there is symmetry. There is asymmetry. There is no symmetry. So in our case, it is found that this compound here does not have a symmetry. And therefore, if it does not satisfy this condition and only satisfies the superposability of its image, it means that this organic compound is chiral and not achiral. So is achiral. It is achiral. Why? Because it satisfies the condition. It does not satisfy the condition that it should not be superposable with its image. But in our case, this one is superposable with its image and does not have a symmetry. So therefore, our conclusion is, for an organic compound to be called chiral, it's supposed to satisfy, that is, two conditions. The first one is, it should not be superposable with its image. It should never be superposable with its image. The second one is, it should not have a plane of symmetry or should not have a center of symmetry. Those are the two conditions. In a case where you have one that is satisfied and the other that is not satisfied, it implies that the organic compound that you are looking at is achiral. The organic compound that you are looking at is achiral. Is it clear?
Yes.
Okay. For everyone.
Yes.
Okay. So now, I said there is another type of nomenclature that we are going to start. Now, this type of nomenclature is called, how can I call it? It's called the SIP nomenclature. It's called the Kang-Ingold Prenlog system. So it's a type of nomenclature that we're going to use to name organic compounds with reference to the carbons that are going to be asymmetric. The nomenclature that we've been learning all along from chapter, I don't know if I can go chapter 1. That is the nomenclature usual, where you just count the number of carbon atoms and give the chain principal, name the substituent, and at the end of the day, you just say, no, it's going to be 2-methylpropane, 2-methylhexane, etc. Now, with this type of nomenclature that we're going to start studying right now, is nomenclature of three-dimensional organic compounds. Of three-dimensional organic compounds. So in your exam, to just give so can you guys see the sharing? Can in good log SIP?
Yes.
In your exam, whenever you go at the faculty, in your exam, if they give you an organic compound, say nommé avec UPAC, if they give you something like this, and if you call this molecule, say that is at position number this 1, 2, and you call it, let me just write it here. You say this organic compound is going to be called, is it how many carbons? That is 1, 2, 3, 4. So 4, you're going to call it but. Now, because with naming of alcohols, we also have to give the position of the hydroxyl function. Now, the hydroxyl function is at position number 2. Position number 2. If you give this name, if you're to give this name, if they give you this molecule, this one here, and you give this name, and you give this one, it's wrong. It's wrong. Even if you've satisfied the nomenclature rules that we've been doing all along, it's wrong. Why? Because whenever you have an organic compound that is drawn in this, I don't know if I can call it in this way, where you have the wedge, you have the dash, and you have the ones that are on the plane. If you have an organic compound that is drawn, with these three, with a wedge, that is the one in bold, and with a wedge that is in dashes, then you have two that are on the plane. You are never supposed to use la nomenclature usuelle, which is just saying no 2-methylpropane. No. This is where now we come in with a nomenclature SIP. Nomenclature SIP. Can ingod prelog. Can ingod prelog. So this is the new type of nomenclature that we're going to learn. This is a new type of nomenclature we are going to learn. C'est la même chose. It's the same thing, but now we just have another aspect that we're going to add on. There is just another aspect that we are going to add on. So when you are given a compound, where is it? When you're given a compound like this, you say 2-methylpropane. If it's drawn like this, if you can see a wedge, if you don't see a wedge, you don't see the other wedge with dashes, you name it like this, nom usuel. The nom usuel, nomenclature usuel, that is going to be 2-methylpropane. But if you have this type of arrangement where you have a wedge and a wedge with dashes, the nomenclature changes now. This is where we apply what I'm calling the SIP nomenclature. That is can in God a prelog. Now, this nomenclature is based on the principle of atomic numbers and what is more prioritaire in an organic compound. It is based on organic compounds that are prioritaire in terms of their increasing atomic numbers. So in a case where you've been told to say, give us the nomenclature of this one, of course, with reference to the carbon that is asymmetric. They ask you to say, okay, give us the nomenclature of this compound. The nomenclature of this compound would be, the molecules will always be given in dimension, that is like the ones you've seen from the TD. They'll always be given in a dimension, and they'll tell you to say, okay, name this compound for us. So you're going to look at which one is prioritaire. Now, priority comes in the aspect of increasing atomic numbers. So it says, on établit selon le numéro atomique Z, un classement de 4 substitutions de l'atome de carbone symétrique. It is always the carbon that is asymmetric that you are going to consider. If an organic compound does not have a carbon that is asymmetric, it implies that the can-in-God prelog system will not apply, because the can-in-God prelog system only applies for the carbon that is asymmetric. It only applies for the carbon that is asymmetric. And we are looking at it in the aspect of increasing atomic numbers. That is, the highest atomic number gets the first priority, the second one gets the second, the third gets the third, and the last gets the last position. So it is always a rule that the hydrogen atom in 3 dimensions should be arrière. It's a rule that the hydrogen atom is supposed to be arrière all the time. All the time. When you have a hydrogen here, it's supposed to be arrière. You take it arrière. You take it kunuma. You take it kunuma. So now, this is the organic compound that you've been given. Said, name it. Now, the question would be, this carbon compound, this carbon atom here, which is asymmetric, is bonded to 4 different substituents. And therefore, we are calling it asymmetric. And therefore, we are calling it asymmetric. So if it's bonded to 3 different substituents and we're calling it asymmetric, we are going to look at which one has the highest atomic number that is bonded to this carbon here. So we have 3. We have 4, sorry. We have carbon here, we have carbon there, we have oxygen there. Or maybe let me say we have ethyl, we have methyl, we have, is it hydroxyl and hydrogen. So now, amongst these substituents, that is the carbon, that is methyl, ethyl, methyl, hydroxyl, and hydrogen. Which atom has the highest atomic number? That is, if you look at the first one, that is the carbon bonded to the carbon bonded to the carbon, and the carbon bonded to the oxygen. Amongst these compound or atoms that I've mentioned, which one has the highest atomic number? The highest atomic number. Which one has the highest atomic number?
Methane.
No.
Is it methyl?
No. I'm saying carbon is bonded to ethyl, methyl, hydroxyl, and hydrogen. Now, this carbon here is bonded to independently other atoms. This carbon is bonded to carbon. It's also bonded to another carbon. It's also bonded to another oxygen there. And it's also bonded to another hydrogen there. I don't want you to consider the whole function. I'll come in with the whole function later on. But for now, I just want you to understand what this carbon atom is bonded to. It's bonded to, or maybe let me do this.
The oxygen.
So now my question is, amongst these atoms, this carbon, this one here, the one that is asymmetric, which one has the highest atomic number? Is it this carbon here? Now for now, Mr. Ted, I'll come in with a where you just look at the functions and you just say, okay, this one is priority, and you go like that. That one is easy. Now for now, I want you to understand where the buzz comes from. So you look at which one is bonded to the carbon that is asymmetric. The first atom that's bonded to the carbon that's asymmetric, you have carbon here. You have carbon, and it's bonded to hydrogen. I've just written H2. And you also have another carbon here that's bonded to hydrogen and another hydrogen. Oh, carbon. This carbon is bonded to another carbon. This carbon here is bonded to another carbon.
Yes.
And you have this carbon here bonded to another oxygen here. And we have this carbon bonded to the hydrogen. So like I said, it's a rule that always when you're doing this, always, your hydrogen is supposed to be arrière. Always, your hydrogen is supposed to be arrière. it's a rule that your hydrogen is supposed to be at the far end. In other words, in the prioritaire, the hydrogen is supposed to be the last one. The hydrogen is supposed to be the last one because hydrogen only has an atomic number of 1. There's no other element or atom on the periodic table that has an atomic number of 0. It's only hydrogen that has an atomic number of 1, and it's for this reason why we are going to say hydrogen is supposed to be arrière toute fois. Now, in our case, we have a carbon bonded to 4 different substituents, and it's making it asymmetric. That's the definition of a carbon that's asymmetric. A carbon that is bonded to 4 different substituents is called carbon asymmetric, or bien a stereo center, or bien a stereo center. Now, we are saying for us to apply the can-ingot prelog system, we are supposed to look at the adjacent substituents and what atom is bonded to the carbon that is asymmetric. Then we are going to look at which one has the highest atomic number, and that is going to take priority number 1. The one that has second highest atomic number will take priority number 2. The one that has a highest, the third atomic number will take priority number 3. Then the last one, which is hydrogen, only has a priority 1. We are going to assign it the last priority. We are going to assign it the last priority. Now, in our case, the question was, which one has the highest atomic number? That is carbon bonded to oxygen, carbon bonded to another carbon, carbon bonded to another carbon. So which one has the highest atomic number here between the 3? 1, 2, 3. Hydrogen is already number 4. So don't worry, hydrogen is already number 4. Hydrogen is already number 4. Hydrogen is already number 4. So which one has the highest atomic number here? Which one has the highest atomic number?
Oxygen.
It's oxygen. It's oxygen. So it's oxygen. So this one becomes our number 1. This becomes number 1. This becomes number 1. Now we are going to look for number 2 and number 3. We're going to look for number 2 and number 3. Now this is what you do. I'm doing this just for your understanding, but with time you get to apply this very, very quickly. So I'll draw this as carbon with a hydrogen there, another hydrogen there. With another carbon, with another hydrogen there, with another hydrogen there. It's the same ethyl, it's the same ethyl. I've just expanded it. This is formula, is it développé plane? Is it développé plane or semi-développé plane? Huh? Is it développé? C'est développé. Oui, c'est développé. C'est développé. So the question still is, we are looking for the one that has the highest atomic number. We are looking for the one that has the highest atomic number. So we have a carbon bonded to a carbon. We have a carbon bonded to the carbon. Now, the atomic number of carbon is what? Atomic number for carbon is what?
12.
Atomic number for carbon is 12. Was it here? No, I don't mean mass. I mean atomic number. It's 6. The atomic number for carbon is 6. So we have this one here that has an atomic number of 6, and this one also has an atomic number of 6. Then what we do is, what we do with the can-log, is it the can-ingot prelog system. If you have 2 that have the same atomic numbers, if they are similar, we go to the other atoms that are bonded to this carbon. So we have this carbon. Now we move, right? You should follow me properly. We have this carbon bonded to this one, right? So we're saying, which one has the highest atomic number here? So we say this one has 6, and this one also has a 6. Okay, if they all have 6, let's forge ahead. Now, it's not going to be this carbon we're going to look at. It will be this carbon bonded to the other atoms. Now, this carbon atom here is bonded to hydrogen, and it's also bonded to another hydrogen and to another hydrogen. So, in other words, you have 3 hydrogens here. We have 3 hydrogens here. We have 3 hydrogens there. And they all have atomic number 1, 1, 1. They all have atomic number 1, 1, 1. Now you go on the other side. We have a carbon here that is bonded to another carbon, that is bonded to a hydrogen and to another hydrogen. Is it making sense? You have a carbon here that's bonded to this other carbon, and it's bonded to another hydrogen and to another hydrogen there. Now, the atomic number of hydrogen is 1, and the other atomic number of hydrogen is 1, and the atomic number for carbon is 6. The atomic number for carbon is 6. So in other words, this one takes priority number 2. Why? This is where I'm coming. Priority number 2. Why? This is what I'll do. If you've noticed, this one here has 3 hydrogen substituents. This one has 3 hydrogen substituents, and they all have atomic 1, 1, 1. Now, fortunately enough, this one here has got 2 hydrogen substituents. Please, you don't add, you don't add. Don't say no, CH3, you add D3, 1 plus 2 plus 3. You don't add. You're just looking at atomic numbers. So this one has atomic number of 1, atomic number of 1, atomic number of 1. So we say, okay, we're going to consider for this one here. Okay, 1, 9, now 41, same. So, okay, 40, 1, now 41, same. Now you go to the other substituent. 1, number 6. You get what I'm saying? Is it making sense? There's 1 here, and there's 1 with 6 here. Or maybe let me do this. We'll correspond this one here. And let me change the character. I'll say this is prime, and this is also prime. I'll say this is double prime, and this will be triple prime. This will be double prime, and this will be triple. So please take note. The reason why I'm putting prim is just to show the differentiation. It's nothing to do with, no, this is how you're supposed to do it. No. It's just a differentiation. So we are saying this carbon here, we are no longer concentrating on the carbon that's asymmetric, not to push carbon asymmetric. Now we are here on this carbon here. We're looking at which one is prioritaire. So we're saying this carbon here is bonded to hydrogen hydrogen prim. And we have another carbon here bonded to hydrogen prim. So, and it has an atomic number of 1. Now, put the atomic number 1. C'est la même chose. Ça change pas. We come outside, we have hydrogen, and it's bonded to 2. Oh, not 2. It's this carbon is bonded to another hydrogen. That is hydrogen prim. Hydrogen prim à l'ordre 2. And it's also bonded to another hydrogen here at order 2. So it's still the same thing. C'est la même chose. The atomic numbers there are the same, 1 to 1. Now we have another one here. We have a carbon bonded to a hydrogen that is at order 3, and it is bonded to Okukumbi. The carbon is bonded to another carbon at atomic number 6. So between the carbon and hydrogen, which one has the highest atomic number? Between this carbon and this hydrogen, which one has atomic number that is the highest? Which one has atomic number? Exactly, the carbon. So it's automatic that this substituent will be position number 2. It's automatic that this substituent will be position number 2, and this one will take position number 3. And we said the hydrogen is always supposed to be at the end, at the the wedge with dashes, always at the end, always at the end. Now the nomenclature comes in this way. The nomenclature comes in this way. So if you have a clock, if you have a clock, you have your hands like that. You have your hands like that. I'll just use one. If you are moving in this direction, what do you call this direction? If you're moving in this direction, what do you call this direction? Clockwise or anti-clockwise? Please.
Clockwise.
If you're moving in the clockwise direction, we are going to name this R. If you're moving in the anti-clockwise direction, it shall be called S. So, number, upper nomenclature number yachinja. So, if we name this compound here, so let's name it. This is the function. This is the function, the hydroxide function, and therefore it means when we're counting, we start from the function and go to the longest chain. So this is position number 1, and we have 2, 3. So yaraba projane. Let me use this one. I'm counting like this. This is 1, this is 2, this is number 3. So it's propane. It's propane. Now it's an alcohol. So it will be propa. No. So at position number 1, what is the hydroxy? The hydroxy is at position number 1. So you say all. At position number 1, all. I know I didn't teach the alcohol nomenclature. It's not that difficult. It's how simple it is. Then we have a substituent at position number 1. We are going to have methyl like that. So, like I said, la nomenclature usuelle. If this was not drawn to a scale of 3 dimensions, when I say 3 dimensions, whenever you see a wedge, it's 3 dimensions because it's showing you that there's this function that is coming out of the page. There's this one that is on the plane, and this one that is behind the plane. You get what I'm saying? If you have this type of orientation, it means you are talking about or you are discussing on a molecule that is in a 3D dimension. So this nomenclature, if you're to give this nomenclature on your exam or wherever you go, if you're working for the International Union of Pure and Applied Chemistry, this one will be wrong. It will be wrong. Why? Because you're not respecting the 3D orientation of this organic compound. Now we are saying, if you are moving, if you are done with a priorité system, which you are seeing here, So we are saying the oxygen came first, then the carbon from the is it ethyl came second, then the carbon from the methyl came third, and the hydrogen at the end. So just add on what Mr. Ted wanted to ask on. In other words, what it is that as you progress in the alkyl groups, if you have an ethyl, let me say you have ethyl, propyl, what comes after propyl? Butyl, and the last one, methyl. If you have a compound and you have these 3, or is it 4 different substituents? If you have these 4 different substituents, the order, please, it's very simple. The order will be butyl will be the first one, propyl will be the second one, ethyl will be the third one, and methyl will be the last one. If you want, you can still draw the carbon, you do carbon, you do carbon, hydrogen, all those things. But at the end of the day, you still find that the butyl will have priority over the propyl, and the propyl will have priorité sur the ethyl, and the ethyl will have priorité sur methyl. It's an order. So for you guys that, okay, because this is the first time I'm introducing this, I was not supposed to introduce that. But now that you know, it is going to be easy for us to just say, okay, if oxygen is the one that has an atomic number of 8, and it's the greatest. If you look at, this is carbon and this is also carbon, so it will be that this one is going to take position number 1, and we are saying the ethyl has priority over the methyl, so this is going to be number 2, this will be number 3, and our hydrogen will be number 4. Now we get back to the nomenclature. So because our orientation of this molecule, our orientation is in this way. This is number 1, this is number 2, and this is number 3, and this is number 4. We are moving in this direction. I want you to follow. We are moving in this direction. This is number 1, number 2. We are coming to number 3. We are coming to number 3. We are going through to number 4. What type of rotation is this? What type of rotation is this? We are going like this. 1 to number 2. Number 2 here, number 2 here, number 3 here, number 4 is here. Number 1 is below there. So I'm moving in this direction. I'm using the same priority. I'm moving in the 1, 2, 3, 4 direction orientation. So I'm saying, what do you call this type of using this orientation for the clock? When you're moving in this direction like that, what do you call this? Is it clockwise or anti-clockwise? Is it clockwise or anti-clockwise? Is it clockwise or anti-clockwise? You people. It's a
Anti-clockwise.
It's anti-clockwise. It's anti-clockwise. And we said, if you are moving in the anti-clockwise direction, we are going to name the organic compound with the S here. We are going to name it with S. Then if you're moving in the clockwise direction, it will be called R. Therefore, the nomenclature for this one will be S in brackets with a dash. So if you've noticed, the only thing that changes with the ingot pre-log system is the orientation of the carbon that is asymmetric. Is it going in the anti-clockwise direction in order over the priorities? Or is it going in the anti-clockwise direction in order over the priority system? So is it clear with this example here? Is it clear with this example? Because this is where most of the people get confused with stereochemie, but it's a very easy maneuver. Is it clear? So we have the S orientation, that is the anti-clockwise, and the R orientation, which is the anti-clockwise. So is it clear with this one?
It's 1 o'clock.
Yes, it's clear.
For me, I'm just a bit behind on how you came up with the name.
Oh, with the name. With the name. Okay, let me just draw it properly. As in, we can draw it in this way. We are saying there is a CH2 here.
No, not that one.
This one.
Yeah.
Yeah, that's where I'm going. That's where I'm going. I want to draw the structure properly so that we count together. So we have a carbon there, and this carbon is bonded to hydroxide, and it's bonded to a substituent, that is a CH3. And we have a hydrogen. We have a hydrogen. So I'm saying this is an alcohol. I didn't do nomenclature on alcohols, s'il vous plaît. I did not do nomenclature on alcohols. So I'm saying nomenclature on alcohols, you start from the function. This is where you start from. You don't start from, no, you don't start, no, is it the chain that is going to belong? But you still apply the same principle, a chain principle and other things. But where you start from, when you have an alcohol, you have carboxylic acid and aldehyde, you always start from the function, just like the way you were starting from the double liaison, triple liaison, c'est la même chose. So our alcohol is at this position. So our counting would be, either we go in this direction, or we go in that direction, or we go in the other direction. But the rule is we are supposed to look for the chaîne principale, la chaîne principale. Now our chaîne principale from the alcohol would be, this is carbon number 1, carbon number 2, and carbon number 3. Carbon number 1, carbon number 2, and carbon number 3. Now, what do you call an alkane with 3 carbons? It's propane. Take. Mr. Chavo, Mr. Chavo. Is it propane?
Yes.
Exactly, it's propane. Now, it's an alcohol. It's an alcohol. So, if it's an alcohol, on supprime la terminaison E. We forget about E. And we add the terminaison, that is the suffix, ol. It's an alcohol. We add ol. Now we are saying for alcohols, we always put the position of the hydroxyl function. Is that position number what? Is that position number what, boss? Boss. Boss. Is that position number what? The alcohol function or the hydroxyl? Is that position number what?
1.
Position number 1. How did you find 1? It's because when we're counting, we said this is our carbon number 1 from the hydroxyl. From the hydroxyl, this is carbon number 1. So we have 1 there. 1 there. Then we are saying again, there's another thing that we are not supposed to forget. We have a methyl, and it's still bonded to carbon number 1. So we are saying to be a methyl like that. Then that is nomenclature usuelle. Nomenclature selon can ingot prelog will be, or the SIP method, it will be S contention S. So if you want, you can also put S, but it's the same chose. Like I told you guys, a coefficient of 1 doesn't change anything in mathematics. So you can put a 1 there, or you can leave it, you can just name it like that. C'est la même chose. C'est la même chose. But in a case where you have the is it a substituent that is asymmetric at position number 2, you are supposed to put the position that is number 2. So is it clear with the nomenclature here? So it's going to be called AS, A methyl propanol. AS, A methyl propanol. Is it clear?
I just wanted to clarify, to ask a question on the 1S that you put there. Is the S coming because of where the first carbon atom is bonded to the alcohol, or where is the one coming from?
The one is coming from this carbon atom here. Which carbon atom are we considering for the asymmetric? Is this one, Tef?
Yes.
And it's at position number what? From the hydroxide, at position number what?
1.
Exactly. So it's at position number 1. And that is the reason why. Hey. Now, if the carbon that is asymmetric was at position number 2, we would have put position number 2. Because, like I said, the can ingot prelog system is a nomenclature that is based selon la carbone asymétrique. Selon la carbone asymétrique. Please take note. Maybe tendez à pas. La configuration absolue d'une carbone asymétrique est une nomenclature permettant de décrire l'arrangement spatial des 4 substituants. And cette nomenclature est établie par la règle de séquence élaborée par can-in et prelog, which is the can-in prelog system, which we are using. So it is selon, s'il vous plaît, selon, what is it? Selon la asymétrie carbonée. Is it clear? Once you just master the can-in system, I tell you, when you go to your exam, is it faculty de médecin, faculty de pharmacie, faculty de sciences, when you just master how you do nomenclature on the can-in prelog system, you are on fire. So now this is the demonstration of how we are going. That is the configuration. Is it S and R? So if we are going in the, this is the clockwise direction, we are going to have the R orientation. And if we are going in the anti-clockwise direction, we are calling it the S orientation. Now, okay, we'll save this example for the third day. Now to just wrap up the end of this cours. So now, at the end of the cours, we are going to also look at a nomenclature that we are calling, is it the cis and trans? I think you guys have heard about the cis and trans. Steph, cis et trans. Cis and trans. So for the cis, it is always with a double liaison. It is always with a double liaison. When you look at your lipids, that's those that are doing biochemistry, you find that we have what you call saturated and unsaturated. Les acides gras saturés et insaturés. The insaturé or bien unsaturated hydrocarbons, that is for the fatty acids, will always contain a double liaison. They always contain a double liaison. Now, you find that there are some that are oriented in the cis manner, and that some that are oriented in the trans manner, Now, what is the difference between the cis and the trans? So the cis is always used when you have two substituents. You have two substituents that are similar and are occurring on the same side. Now, when I mean two substituents that are similar, I mean this type of orientation. What is this? The substituents, they are similar. Concept here. They are, again, in other words, I can go desubstitute. They are similar, like that. Even here, they are similar. They are also similar, even though they are on the other side, but they are similar. Like on both sides, they are similar. Like if I was to bring a mirror here or symmetry, this is exactly equals to this one, and this is also exactly equals to this one. This is what I mean by they are similar. Is it clear? Because it's going to change a bit, Panonapa. Is it clear with this part? Where I mean, when I say they are similar, I mean what you have on your left hand here is also equals to what you have on your right, but maybe the orientation might be different. That is, the one on your left here might be below, and the one on your right might be on top. But at the end of the day, what you have on your left is exactly the same as what you have on your right. Is it making sense? Before we go to the nomenclature now.
Yes.
So what you're having on your left here is the same as what you're having on your right. Even if the orientation is different, even if I was to bring this one here, c'est la même chose. It's still the same thing. C'est la même chose. C'est la même chose. Now, the cis orientation comes in when you have two substituents that are exactly now similar, if they are very similar, about a double liaison. You only use this one when you have a double liaison. When you have a double liaison and the substituents that you have are similar, that is methyl. I'll give another example. If you have R1, I'll use R1 and R2. And if R1 and R2 are the same, si R1 soit AR est égal à R2. If they're similar, they are same. We could put beta and beta as well. So these two are also similar. Now, it is always about a double liaison. It is always when you have a double, always when you have a double liaison. If you have this type of orientation or an occurrence where you have two groups, ou bien, I'll just read, la configuration 6, où les deux groupements méthyl sont du même côté de double liaison. La configuration 6, où les deux groupements méthyl sont du même côté de la liaison. If they are on the same side, that is of the double liaison, we call it a cis configuration. We call it a cis configuration. Now, when you have la configuration trans, où les deux méthyls sont pas du même côté de la double liaison. Ils sont pas du même côté de la double liaison. On change. Now you have a methyl on the other side of the liaison, and you also have this one on the other side of the liaison. So in other words, when you have this type of orientation on a double liaison, you call it a cis. And when you have this type of orientation for a double liaison, we call it a trans. And please take note, if the substituents that are we are talking about are similar. We only do that. We only put the cis and trans if they are similar. If they're not similar, but you have a double liaison, we apply another rule now. We apply another rule. Another rule. Now, is it clear with the cis and trans? And the nomenclature still remains the same. It will be called but de in. Now you just put, is it a cis orientation? Are the substituent on the same side? Or is it a trans orientation when the substituents are on different sides? So the position that is going to be 1, 2, 3, that will be but de in, ou bien it will be 1, 2, 3, 4, it will be but de in. Now with a different orientation. This one here is trans because we have two substituents that are similar. Now they are in opposite directions. And this one will be called cis but de in because you have two substituents that are the same and are on the same position, or maybe say même side, même côté de la double liaison. Is it clear? Est-ce que c'est clair? Est-ce que c'est clair?
Oui.
Oui.
Pour tout le monde, c'est clair? Pour tout le monde, c'est clair?
Oui.
Okay. Then to just summarize,
Oui.
le dérivé trans est plus stable que le dérivé cis en raison de la faible interaction entre les deux groupements methyl. So, for those that will go in advanced organic chemistry, you're going to look at steric hindrance. So, because of steric hindrance, you have this one to be unstable as compared to this one. So, I won't go as deep as steric hindrance, but for those that will go in deep for organic chemistry, there's what you call steric hindrance. Then we have isomérie cis-trans ne peut s'appliquer que si l'on a le même substituant sur chaque atome de carbone éthanolique. What they mean by éthanolique is just a double liaison. A double liaison that is in this type of orientation. A double liaison that is this type of orientation, that is carbon éthanolique. And another thing I forgot to mention, on a carbon that is asymmetric, or I'll mention it when we look at another exercise on a can-in-log pre-log system. When a carbon is involved in a double liaison, it is never supposed to be taken as a carbon asymmetric. If it is engaged in a double liaison, we are not supposed to take it as a carbon that is asymmetric. Yeah, that is just one thing I forgot to mention because we're going to apply it in the exercise suivant. Now, there is what you call la isomérie géométrique. Now, with the Z and E, what do you call it? Z and E orientation. So Z stands for Zusammen and E stands for Engagen. They are German words. So with this one, other than using the cis and trans, it's still on a double liaison. Other than using the cis ou bien le trans, on va utiliser Z and E. Now the question is, how do you know that we're going to use the Z or we're going to use the cis? So, or the Z ou bien le E. So here are examples. Now, for us to classify that, okay, this is a Z and this is a cis orientation, first of all, you're supposed to look at them in this way. If you have two substituents that are occurring and they are similar, that is on both ends, this one here and this one, they are similar, of course. And what you have on the bottom is also similar to this one on the other side. If there's bromine, and you also have bromine here, we would not have used the Z or E nomenclature. Please take note. If the two substituents, that is methyl, bromine, if that was the organic compound that we are studying here, if that was how it was supposed to be, like if that is what we are seeing here, we would have used the cis and trans orientation. But in our case, it is found that we have different substituents. La nomenclature E et Z s'applique à tous les alcanes ayant les substituants différentes sur chaque couche de carbone sp2. So ethanoic carbons. That is the ones that have got double liaison. That is 1 pi bond and 1 sigma bond. 1 pi bond and 1 sigma bond. Et ayant des substituants différents. Et cis trans ne peut s'appliquer que si l'on a le même substituant sur chaque atome de carbone ethanoique ou bien à hybridisation sp2. Is it clear? Please, these two, that's why I also underlined. Même substituant sur chaque atome de carbone ethanoique. This one is ayant des substituants différents sur chaque côté ou bien sur chaque atome de sp2 hybridisation. C'est clair on that part? On that part, is it clear? You use the cis when you have the mem, if they are the same. You use the tron, you use the E and Z when they are different, when they are different. C'est clair? I heard someone with the question.
The network was breaking. I'm sorry. Can you please explain?
Okay.
Starting from where you started on Z.
Here. On here. On Z. So we are saying, before I even go on Z, we're saying you only use cis ou bien trans. La isomérie cis ou bien trans ne peut s'appliquer que si l'on a le même substituant sur chaque atome de carbone ethanoique. If they're the same, like I said, they can be the same. This is methyl, and this is methyl, and this is hydrogen, this is also hydrogen. They are the same. It's just that the orientation is different. But in a case where you have the substituant est différent, totalement différent, sur chaque côté de la carbone ethanoique ou bien carbone à hybridisation sp2, we are going to use the Z and E nomenclature. The Z and E nomenclature. And therefore, we are going to now apply encore the can in a prelog system. The can in God a prelog system. So examples are, I gave examples here. So you have this compound here. I said, in a case where you had a bromine here and another bromine here, we would not have resorted to the can in God or bien the Z and E system because we have la même substituant, même côté, that is if we had the bromine here. But in this case, we have la même substituant, oui, même ils ne sont pas la même de l'autre côté. Ils ne sont pas la même de notre côté. Alors, on va utiliser le Z et E system. So in our case now, if we're using the Z and the E system, we are going to apply the can in God prelog system. The can in God prelog system, which is the priority system where we have which one is appearing with the highest atomic number, second highest atomic number, third highest atomic number, and the least atomic number. So there are cases where you will not have hydrogen. There are cases where you will not have hydrogen. But please take note, the lowest priority will always go to that one that has the lowest atomic number. In a case where you have methyl, propyl, butyl, is it pentyl? It is methyl that will be there at the end. It will have a priority of number 4 because in the priority chain that is pentyl, butyl, propyl, methyl is the least priorité. It is the least priorité. So in other cases you have hydrogen, in other cases you will not have hydrogen. So please take note. So in our case here, we have bromine and we have, this is ethyl. Now the question is, for us to determine which one is prioritaire ou bien, prioritaire ou bien on va utiliser quel, is it Z or S? So if they are at the same side, if the substituents are at the same side, if the substituents in question are at the same side, and when we calculate or find out that the priority of one is on our right or on the same side, let me say on the same side, and we find that the other one is Chiralité and is found on the other side, we are going to use the Z and E system. Now, in our case, we have the substituents that are different, or bien that are different at the same side. We have two substituents that are different at the same side. So we're going to consider at which carbon atoms are they bonded to? At which carbon atoms are they bonded to? Now we have, this is carbon number. We can, so because brom is number 1 when you're doing a nomenclature. So this is going to be at position number 2 because la chaîne principale doit être qui a plus de atomes de carbone. So chaîne principale will either be this one here or it will be this one here. But we are supposed to take the liaison into consideration. Therefore, la chaîne principale doit être celui-là. So it will be this one here like that. Now, carbon number 2. This is number 1, number 2. This is number 1, number 2. Carbon number 2 has got two substituents. Carbon number 2 has two substituents. That is the bromine and the methyl. The bromine and the methyl. So, like we were saying, this carbon here is bonded to another carbon. It's also bonded to another bromine. Which one has the highest atomic number? Is it bromine or carbon? Is it bromine or carbon?
It's bromine.
It's bromine, right? It's a bromine. It's bromine. So please, every time you're doing the Cannon-Gottpillock system, always put this in your mind that what we mean is something like this, something like this. So see carbon, I'll just put H3 on, you get what I mean. And hydrogen there, another hydrogen there. So this is what I mean, huh? This is what I mean. And another hydrogen there. So, which one has the highest atomic number? Is it this carbon here and this bromine here? So it's the bromine. Someone said it's the bromine. So the bromine has priorité sur this carbon here. So this is what you're seeing here on my presentation. This is what you're seeing on my presentation. The bromine has priorité sur le methyl. It has priorité sur methyl. Ou bien les carbones, c'est la même chose. Now, like I said, in the chain of, in the enchaînement of the substituents, methyl, propyl, butyl, pentyl, hexyl, ecosyl, all those things. As the number of carbon atoms increase, priority also increases. So in our case, I mentioned this, the ethyl would be prioritaire sur le methyl. The ethyl will be prioritaire sur the ethyl will be prioritaire sur le methyl. That is what we have here. So our ethyl is prioritaire sur le methyl. And it is found that the two substituents into consideration or in consideration are found on the same side. They are found on the même côté. Se trouve à la même côté du liaison de carbone. C'est-à-dire, on va utiliser Z. 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 So even the nomenclature now, it's just like what we're just from doing. Instead of us putting the S and Shinganan, we are going to put the Z in capital letter, of course, Z, and the name will be position number 2, bromo, 3, methyl, pent 2, in. 2, bromo, 3, methyl, pent 2, in. Methyl, pent 2, in. Now, what about in a case where instead of us having our CH3 there, let me just change this so that if we had this type of orientation, because we have two different substituents found on the other side, sont pas trouvés à la même côté. We have this one here that is also different from this one. We are going to use the E and Z nomenclature. But if we had the same on the other side, that is, if we had a chlorine here and another chlorine, we would have resorted to the cis and trans nomenclature. I hope it's making sense. Now, if you have two different substituents, that is about a double liaison, that is a carbon with sp2 hybridisation, we are going to apply what we are calling the Zusagen ou bien Engagen. Zusamen ou bien Engagen. If the two substituents are either found on the same side, that is if they're different, and if they are found on the other side, that is if they're opposite, we're going to use the E nomenclature. So in the same sense, because the bromine and the methyl or the ethyl were found at the same site, we applied the Kahn-Ingot Prelog system, and we found that the bromine has a priorité sur the methyl, sur le methyl. Now, we went to the other side and found that the ethyl also has priorité sur the methyl, sur the methyl. And therefore, we said because the two substituents which are different are found on the même côté, they are found on the same side. They are found on the same side. Il s'agit d'une isomérie Z à l'amande Zusamen. Then, in a case where you have the same orientation as this, now I just changed pali bromine apanekapo chlorine na methyl yende pamwamba. You have your chlorine there, and you have your ethyl pamolo there. You have your ethyl pamol. What I said was, in such a type of nomenclature, you are going to use E, which is what is it? You're going to use isomérie E à l'amande Engagen, qui signifie la opposée. It means they are in the opposite direction. In the opposite direction. And therefore, the name will be, c'est la même chose. In the place of bromo, you just put chloro. Say chloro, it will be 2 chloro, 3 methyl, 2 in. But not forgetting that, because this is a double liaison, and the isomery that we are looking at in our case is either E or bien Z, and because the substituents are found on different sides, we are going to use E. We are going to use E. So the nomenclature for this one will be called E de chloro chloro 3 methyl pent de, in, like that. 22, in, 22, in. So this marks the end of nomenclature and all the notions that you guys are supposed to know for your organic chemistry. Yeah. So are there any questions so far? From everything that we've done today?
Yeah.
Okay. What's the question?
I don't know. Let me just say it in my own way. In my own way, it's what you
Boss, Enantiomere is cutting. Enantiomere is cutting.
no.
Huh? Enantiomere is cutting. Or maybe just me. Let me, while Kondwan is still looking for network, I can just give maybe another example on the same to just solidify. So still, is it now we have 4 different substituents that are very much different from the other. So we have one here, we have another one there, we have another one there, we have another one there. So we are saying we're going to apply the Z and E nomenclature. We're going to look at which one is priorité over the other. So in our case, we have, I'll start with this one, this side. So what you guys are supposed to note, maybe a trick I can just guide you on when you're applying your can-in-God prelock system. Don't always consider, I know with time, with practice, I mastered this art. But with time, like let's you're still learning how to do it, you break the carbons like you've seen here, what they've done here. You break the carbon and say how many carbons are going to this carbon, how many carbons are going to this carbon. But for me that has done this over and over again, there is no need for me to look at the carbons. This is what I do. There is no need for me to look at all these carbons. What I just look at is this and this. Now, hydrogen, automatically hydrogen is going to be overruled because hydrogen has an atomic number of 1. Now, between chlorine and oxygen, which one has got priority? Which one has an atomic number that is greater?
Chlorine.
Exactly. So chlorine is priorité sur this one. That's a trick I mastered. Here, you already have a ethyl, and I said ethyls will always be superior over methyls. Automatically, this one is priorité. And we have 2 substituents found at different sites. That is, at 2 different sites. We have our nomenclature E. Nomenclature E. So please, as in the hassle of doing the carbon, like what you're seeing here. What you're seeing here, with time, you'll be able to look at, okay, say, no, this one is superior over this one because there's a chlorine there. This one is hydroxide, it is superior over all those things. So, same applies to this example here, this example here, this example here. So, you have a carboxylic, now here, I'll take it in form of functions now. I'll take it in form of functions. You have a carboxylic function, and an alcohol function. Now, between the carboxylic function and the alcohol function, in our nomenclature, even though we didn't go as far as naming carboxylic functions and all those things, but I guess you guys heard me say the carboxylic function has priorité to all of them, be it anhydrides, be it amides, be it aldehydes, be it ketones, be it alcohols, be it thiols, be it ethers. The carboxylic function has priorité. All of them are more priorité. They are less. So other than counting, say carbon, you just look at the functions. The carboxylic function is priorité to the alcohol, and therefore you count it in. And when you look at benzene and this one here, this is 1, 2, 3. This should be isopropyl. With this one here, 1, 2, 3. You'd be like, no, this is just an alkyl. This is an alkyl. This is an alkyl. Then, Mr. Kondwani, this is where I come in with the question that you asked me later. Or there's a question you asked me. You say, there's what about phenyl? So phenyl, this one can be called phenyl when you consider this thing here. This line here, if you consider it. You call it phenyl, ou bien you can call it benzene. You can call it benzene, c'est pas grave. You can just call it benzene. Now, between benzene and is it what's this? Isopropyl. Which one has priority? Which one has priority? Which one has priority? It's the benzene ring, of course. The benzene ring has priority over this alkyl, and therefore we have them at the same side. Our nomenclature will be called Z. Our nomenclature will be called Z. So it's an art that I've mastered over a long time with practice, of course, with practice. So what I'm trying to say is, you can only master this if you practice. You can't just master it. No, this shani, no. Practice, with practice. So if there are no questions, this marks the end of organic chemistry. So the organic chemistry that I've taught, please, if you just practice it very well, when you practice it very well with examples, I'll do a TD later on with examples. That is on stereochimie. Stereochimie is the most tricky part where people find a little bit of challenges. Stereochimie is the tricky part, but on the others, Newman, maybe Newman as well. But stereochimie, the whole of stereochimie is the trickiest part of organic chemistry. But if you've mastered how you go about, is it représentation de Cram, représentation de Fischer, représentation de Newman, when you come to isomérie de conformation, isomérie de configuration, is it isomérie de Z ou bien E ou bien cis ou bien trans, is it application de la is it carbon absolu, configuration de can ingot prelog system, all those things. If you just master that, for organic chemistry, you are warm and dry. So if there are no questions, this marks the end of our class for organic chemistry. So other than doing a TD today, I have decided, I was supposed to end everything today. I have decided that, okay, we are going to do a TD tomorrow, so that if there are any questions from anything that you've learned so far, we will address it now. Then tomorrow, we end with a TD. So from everything that we've done, from nomenclature, from représentation spatiale, from isomérie et stéréoisomérie, from diastéréoisomérie, ou bien, what you call it, the Z and E configuration, all those things. Are there any questions from all the things we have done? From all the things that we have done, est-ce qu'il y a des questions? D'accord. I guess there are no questions.